Hi everyone, this is Math4Uni, and this is the worked solution to question 9 from the worksheet of Lecture 2 from our online Udemy course, the link of which is in the description. Please consider liking and subscribing if you found this content helpful. So, the question says, prove that E is irrational. And on the worksheet, there is a hint that says, write E equals P over Q, use Taylor expansion, and consider Q factorial times E. So, let's break this down by using the steps from the hint. We want to prove that E is irrational. And so we can start by assuming the opposite and attempt to get a contradiction. We start by writing E as P over Q, where P and Q are integers as usual, and Q is not 0. Next it says to use Taylor expansion, and by this it means write out the Taylor series for e to the x, which is 1 plus x squared over 2 plus x cubed over 3 factorial, and so on. The general term of which is x to the n over n factorial. If we put in x equals 1, this gives us a series for E. We have E equals 1 plus 1 plus 1 over 2 because 1 squared is 1, plus 1 over 3 factorial because 1 cubed is also 1, and so on. Now, the next part of the hint says to consider Q factorial times E. But first, let me motivate why that will be helpful. If we continue on this series expansion, then we would have 1 over Q minus 1 factorial somewhere, plus 1 over Q factorial, plus 1 over Q plus 1 factorial, and so on. Again, because all of the x to the n's are just 1 for x equals 1. Now, if we multiply by Q factorial to both sides, then we will have Q factorial for the one that's here, then Q factorial for the second one that's here, then Q factorial over 2, or 2 factorial, same thing, plus Q factorial over 3 factorial, and then so on, all the way up to these terms here, which give us Q factorial over Q minus 1 factorial, plus Q factorial over Q factorial, plus Q factorial over Q plus 1 factorial, and so on to infinity. The useful thing about doing this is that a lot of these terms are just integers. In particular, Q factorial and Q factorial are, also Q factorial over 2 factorial, because 2 factorial is secretly hidden inside Q factorial, and this is the same for the same reason all the way up to this term, and then finally this term, which is 1. And so all of these terms here are just integers. And so this is equal to some integer, we're not sure what, plus, and then this next term here gives us 1 over Q plus 1 by expanding Q plus 1 factorial, as Q plus 1 times Q factorial, and hence dividing out the Q factorials. The next term would be 1 over Q plus 1 times Q plus 2, and then so on. So if we look at the remainder terms, i.e. the terms that we have after this certain integer at the beginning, then we have 1 over Q plus 1 plus 1 over Q plus 1 Q plus 2. The next one would be 1 over q plus 1, q plus 2, q plus 3, and hopefully you can see how the series continues. Now, let's step back a moment and see where we are. We have q factorial e, which should be an integer because, remember, e equals p over q, and so qe equals p, which is itself an integer, and so certainly q factorial, which includes q, times e, should be an integer if e is rational. So on the left-hand side of the above, here we have an integer. We also have an integer here, and we're just considering what this remainder expression is in terms of whether it's an integer or whether it's some kind of other expression. And so, in particular, if we're aiming to get a contradiction, imagine if we could show that this expression here was not an integer. Then how is it possible that an integer is equal to an integer plus something that's not an integer? Because if it's not an integer, say it's 0.5, then we'd have an integer, say 2, equals an integer, say 3, plus 0.5. How would that make any sense at all? That 0.5 is a problem. And so let's look at what kind of form this expression can take and hope that we can show that it can't be an integer. So we have that the expression looks like this for the first few terms, and it continues in exactly the same way. The next term would be 1 over the product of q plus 1, q plus 2, q plus 3, q plus 4, and so on. Now, we can't easily actually calculate this sum, but we can use an inequality to turn it into a series that we do have familiarity with calculating. So if we look at the remainder expression, we can apply an inequality to each term in order to evaluate the overall series. So the remainder is less than or equal to 1 over q plus 1, which is literally the first term, but then the second term, we can use an inequality to get 1 over q plus 1 all squared. This is because 1 over q plus 1, q plus 2 is less than or equal to 1 over q plus 1 all squared, because q plus 2 is greater than or equal to, well, it's certainly greater than q plus 1. And therefore, by proceeding in exactly the same way for the next term, we would have plus 1 over q plus 1 all cubed, and then so on. Now, this expression here is a geometric series with first term 1 over q plus 1 and common ratio 1 over q plus 1 as well. And so the sum to infinity will be 1 over q plus 1 times 1 over 1 minus 1 over q plus 1, which if you expand out by bringing this q plus 1 into here, we get 1 over q. And therefore, the remainder is less than or equal to 1 over q. Now note that e is not an integer itself. We know that e is strictly between 2 and 3, and we can identify this by looking at its Taylor series. Since it's not an integer, we can assume that q is not equal to 1, because we've written e as p over q, and so if e were an integer, then we could write it as p over 1. But because it can't be an integer, we can assume that q is not equal to 1. And therefore, we can say it's 2 or minus 2, but it's certainly not 1 in modulus. And therefore, this is strictly less than 1. Now, we can further assume that Q is positive by taking P to also be positive, and hence the overall remainder expression is strictly between 0 and 1, and therefore it certainly cannot be an integer. Hence, Q factorial times E is not an integer either, because it's equal to the sum of an integer plus this remainder, which is between 0 and 1. And therefore, Q factorial E cannot be an integer, and this is our contradiction. Hence, we have shown that E is irrational. Now, I know that this proof is slightly strange. Please go through it again, potentially on paper, reproducing each step, and eventually it will click. If you've enjoyed this content, then please consider liking and subscribing, all that great stuff, and also check out our full Udemy course, link is in the description. Thanks for watching, and goodbye for now.